use the features of amphiphilic molecules. So they are also in this triangle somewhere, and they are very important for our lives, of course. And an example for colloid is a blood cell. So these, I mean, this is just to give you an impression of what soft matter physics is and why it is relevant for biophysics. And so this feature, and the important feature is that these energies of the order of the thermal energy can do something with the system. And then you ask the question as a physicist, how do we model that? That this stuff is under the influence of thermal processes and thermal energy all the time. And the question put differently is how to model the interaction with a surrounding medium. Imagine here you have a colloid, a 1.5 micrometer particle, and then there are surrounding fluid molecules, and they are much smaller, but not too much smaller. So when and they hit the particle randomly, and once in a while, a lot of them hit it and it moves a bit in this direction. How do you model this system? So of course, we all know Newton's second law, mass times acceleration is the force. So if I wanted to understand the dynamics of this particle, I mean, if you look at Newton's second law, you say, okay, I take all these particles, I have all these water molecules, I have this one colloid that I'm actually interested in. I write down the forces with which they interact. I write down all the initial conditions. Where's this particle? Where's that particle? What are their velocities? And you could then solve these equations, and then you would get the trajectory of this colloid that you're interested in, right? But the problem is, this is, of course, you can never do it because you have 10 to the 20 water molecules, and so there's a lot of them, and you actually don't really care. You don't care if this molecule goes like that or like this. You only care what happens to your colloid. So it's very hard to, I mean, the question you have to ask is, how do I model a colloidal particle, or how do I model these small systems that are in interaction with an environment that can change them? And I don't want to keep track of the environment in detail, but I want its effect on the system I'm interested in a phenomenological way, so to say. And this problem was solved by Langevin in 1908. And he said, or he showed, building on work by Einstein, that the effect of the medium, so here the water molecule, can be modeled by having a special kind of force. So it's a sum of a friction force and a stochastic force. And so here you have the friction force. So you have an acceleration that goes against the current velocity and is proportional to some constant. And this is simply, if the particle moves like this, it will hit the water molecules and this will slow it down. So you have a friction force here. And the other force, the random force, models that if you have these particles here and they have velocities, then once in a while they will kick the colloid and then they will make it move. And so these are the two features that the surrounding medium contributes here to the motion of the colloidal particle. Frictional force and a stochastic force due to the random kicks. And these are both, so this, I mean, this is a stochastic process in mathematical language. And we assume that these random kicks are, the strength of them is Gaussian and that they are uncorrelated in time. And this is quantified here in something called a fluctuation dissipation theorem, which says if you take the random kicks at one time and another, then if the times are unequal, then this delta function is 0. Then the random kicks are uncorrelated. So the medium is very, very fast, equilibrating all the time. And if you look at the variance of this, so at the same time, then the prefactor also has a gamma in here. So in this random noise is also some information about the friction, which is kind of, the idea is that both the friction and the kicking has the same molecular origin. So that's why the gamma appears here. But this is kind of an extension of Newton's equation of motion to be able to deal with these very small mesoscopic systems. And one thing, so this is kind of a complicated equation. You have your acceleration, velocity, typically you're interested in the position. It's a second order equation, right? And if you have a very light particle, or if the particle is light compared to some other time scale, or it's not too heavy, then you can typically neglect the inertial term. So you can cross this out, you bring this on the other side, and then you have the so-called overdamped Langevin equation, overdamped dynamics. And now basically the current velocity of the particle is proportional to the kicks it feels now. So if the water molecules kick the particle a bit in this direction, it will move. But as soon as they stop, it will stop moving. So this is called then the overdamped Langevin equation. And in my talk, I will use this because these effects due to inertia are kind of are not so interesting in what I'm interested in. And also in the experimental systems, I will show you can safely assume that the dynamics is overdamped and that anything that has no force acting on it right now will not move. Okay. And so here is an example. I just simulated this simple Langevin equation 3 times, always starting at 0. And practically, it simply means that at each time step, you draw a random Gaussian number and you add it to your current position. And you see, it's an interesting fact now that because of the stochasticity of the random force, the trajectory itself also becomes a stochastic process. And when you do the simulation twice, similar as when you observe an experiment twice, you will in principle get a different outcome. So you have to work with probabilities of outcomes. Okay. And so, of course, you can also include external forces. So imagine you have a potential energy. And if you don't have any random forces or anything, if you set your particle close to the top, in standard Newtonian mechanics, it would just roll down. And then at some point, if there's friction, it will just lay in the minimum and it will just stay there, right? But if you take the overdamped Langevin equation and you add this deterministic potential, then because of the stochastic force, you can also get out of minima. So here is an example trajectory with a quadratic potential, with a quartic potential energy, and you see the particle stays in the minimum, but it also goes out. So it's kind of interesting because with this random force, you have qualitatively completely different behavior as with standard deterministic dynamics, of course. Just to give you an intuition a bit for how these stochastic dynamics are different from what you know about standard Newtonian mechanics. And this is Langevin dynamics is something very important. So you can basically use it with variations, of course, with any system that is influenced by seemingly random environment. I mean, seemingly, I mean, if you knew all the details of the water molecules here, you wouldn't need this random force. But because you don't know this information, you can model it by something that seems random on your level of description. But if you knew everything, it would, of course, not be random. So it's all classical physics. And so the Langevin equation is used to model, for example, colloids. As I said already, you can model proteins in your body with it. Then interestingly, chemical reactions are also modeled sometimes as Langevin dynamics. So imagine here a reaction has not happened. Here a reaction has happened. And you are asking, what is the time until the reaction happens? So for example, here your milk is not spoiled. Here your milk is spoiled. And you ask, how long does it take until my milk spoils? Then you ask for a chemical reaction rate, and these Langevin dynamics can be used to model that. And for example, one thing you see is that the average time in Langevin dynamics to go over this barrier for the reaction to happen scales like an Arrhenius law. So the time scales like e to the minus 1 over temperature. And this is kind of explanation for why you want a fridge, because if you have a lower temperature, then this number will be larger, so the time will be longer. And so, is this correct? Yeah. No, it's here should be a plus. I'm sorry, it's wrong. So, but the point is, if you have a larger barrier or if you have a lower temperature, then the time you take scales exponentially. And Langevin dynamics is also relevant beyond physics. For example, in finance, people use variations of Langevin dynamics to describe like stocks or other securities or derivatives. So just so to give you an idea, that Langevin dynamics is something very generic and something that has a lot of applications. And this is kind of the tool I'm working with every day, the Langevin equation. And one fundamental question you can have is, of course, what is the probability of an individual trajectory? Say you start at some time here, at some position phi at time initial, and you want to end up at a different position, and you think of this path. You can ask, what is the probability that my stochastic trajectory takes this path? It's kind of similar to asking, when you have a Gaussian distribution, you ask, what is the probability that I draw 1/2 from the Gaussian distribution? And this similar to the Gaussian distribution, if you ask what is the probability to observe this individual single trajectory, it's 0. Just like when you have a continuous probability distribution and you ask what is the probability to observe a single number, it's 0. And people wanted to, I mean, because it's so fundamental, the path probability, people were working or are working on quantifying it. And one thing to approach this question, what is the probability of this path, is to consider not only the path, but a small neighborhood. So here we have again the reference path in black, and as a gray shaded region, you have a small tube around it. And it's a tube in space-time. So here's time, here's position. If you were to think of this in position only, then it's kind of like an interval that moves. In the beginning, the interval is here, and then the interval slowly moves to the final position of the particle. And then mathematicians considered, okay, the probability for this trajectory to happen is kind of asymptotically the probability for a stochastic trajectory to stay in this tube, right? So mathematicians consider x minus phi, so the distance of the stochastic trajectory x from the reference path phi should always be smaller than some radius r. And so here, this is the probability to stay in this gray region. You could also take another path, say, let's take this constant path. We could draw a similar tube around it, and we could ask what is the probability to stay in a tube around this path here. You could look at the ratio, probability to stay in this tube, divided by probability to stay in that tube. And then you can take the limit radius to 0. And you can think of this then as kind of the ratio of the path probability for this path and that path. And the thing is, individually, these things go to 0, because if you shrink the radius to 0, as we will later see is a bit more, the probability for the stochastic dynamics to take this trajectory is 0. So you have here 0 divided by 0, and the ratio is non-zero. And that's what the mathematicians are after. They want to look at the limit of these limits of ratios, and even though the numerator and denominator are 0, the ratio is non-zero, and this then serves as a kind of fictitious density for path probabilities. So this is the definition of the ratio of path probabilities, so to say. Does this make sense? And one problem I had with this, or we had with this, is this cannot be measured in experiment, because basically what you here have at the end is 0 divided by 0, and the probability of this path is 0 in the end. So how do you verify that what you did makes sense? Of course, it's a mathematical proof, but is it physical? Is this really like the ratio of actual physical path probabilities? And then you could argue, okay, I took a lot of effort to quantify things that are 0. Why would I care? If I look at a real physical system and I don't take this path, but I take a path that goes like this and then makes a tiny detour, I probably would not care, right? There's always some kind of threshold up to which I'm interested in my path. So it's kind of a limit to the usefulness of this, I would say. And so what my collaborator Ronojoy and I came up with is, or we asked the question, what happens if we keep the radius finite? So if we look at this tube and we don't take the radius to 0, but we look at a finite radius, this would solve both problems, right? In a sense, we obtain a finite probability, so we obtain something that can be measured. If you run enough experiments, you will see a trajectory that remains in this tube, and you can quantify that and you can verify the prediction. And also it's more relevant in practice, because if you, because as I said before, because you will always not care about small deviations from your reference path. So why not incorporate it in the theory that you don't care? So what we considered then was we wanted to calculate the probability for a stochastic trajectory to stay inside this tube. This is this one, probability of the stochastic trajectory x of t to not go further away than distance r from phi until time t. And this probability is equivalent to the exit rate at which stochastic trajectories leave the tube for the first time. So this alpha is the exit rate, and it describes, for example, at this time, how many stochastic trajectories that have never left the tube until now leave now for the first time, and then they are gone as far as we are concerned, because we only care about those that have never left until now, and we want to know how many we have in the end. So all I want to say is this exit rate from the tube is equivalent to knowing the probability to stay in the tube. And we solved the stochastic dynamics to calculate this for finite radius. And our main result, which I think is very cool, is that this exit rate at which the stochastic trajectories leave the tube is at very small radii, scales like 1 over r squared. And this is kind of like a free diffusion exit rate. So if you have a very small radius tube, the stochastic dynamics doesn't care about any potential energy or anything. It just looks like there's no external forces at all, and it's freely diffusing, and the exit rate diverges. So if you have a very, very small radius, this will become very, very large. So then you have a large exit rate. So this exponential will be very small, and then this will go to 0. So this term ensures that as you shrink the radius to 0, the path probability or the tube probability goes to 0 as well. And then what the mathematicians actually calculated was this term. So when you look at ratios, then as the mathematicians did, they looked at a ratio for this path and that path, then this term cancels, and then they take the limit radius to 0, so everything higher order canceled, and they only get this part. So this is something that mathematicians have derived, and this quantifies the ratio of path probabilities as it is found in the mathematical and also in the physical literature. In our language, it's just a power series term in the exit rate. And the term that we calculated for the first time is now this finite radius correction. So this tells you if you make the radius finite, how do you have to change the exit rate? How is it different from these two terms? And this is what we calculated, and it allows us to actually consider finite radii. So this is kind of the main results of some of our calculation. But but one other thing is, so people typically don't in the literature until now, nobody looked at it like an exit rate. So the whole formulation is kind of new, but this is the actual new calculation, the new result that we got out with this. Okay, so this is a fully analytic calculation. And so we compared it, of course, with simulations. And what we see here is a potential energy that we chose for our dynamics. We have a minimum here, and we consider a path that starts here in this minimum at time 0. And then it crosses over the barrier and it ends in that minimum. So this is signified by this path here. This is the path we want to take. And then in our theory, we consider a radius of 0.5 in our units. Then we can calculate the finite radius exit rate along this path. And basically what we find is this blue dashed line is the exit rate that we calculate analytically. Then we have numerical simulations, which are the of this dynamics of, we can simulate the probability to stay inside the tube, and it's numerically exact. And we find that this is here the light blue line, and it agrees very well with our perturbative analytical results, except for here there's some deviations. And this line that is called Onsager-Machlup here is this result that was known before. So basically what we're saying is, if we take this path in this system with this tube radius, then our quadratic corrections are important, because the difference between the blue dashed line and the black line are exactly these quadratic corrections that we calculated. And here, let me just run the video. So now you see the path traced out, and here's the tube. And here you see the probability density of all the trajectories, stochastic trajectories that have never left the tube until now. So those that remain. And the exit rate tells us which of these are leaving now for the first time the tube. And you see, I think the agreement between the numerical simulations and the analytic results is quite okay. I mean, I think it's good, because if you consider that this is like a nonlinear problem and we're looking at stochastic dynamics and there's a lot of stuff going on. But okay, but the important thing is that the theory that we derived agrees with the numerics, so it describes what it should describe. I think this is the most important thing. And also very important is that if you want to consider finite radii, which are the thing that you can measure in experiments, then you actually need our correction, because having just the classical results is not enough. So these are the two messages of this slide. Okay. And so we had this, and it was nice, our theory worked, but I was saying the whole time, this allows to measure things in experiments, right? So the question was, can we measure these tube probabilities also in experiment? Can we measure the probability for a stochastic trajectory that is measured in experiment to be inside a tube? And so I randomly met Yannis, which was very fortunate that I met him, because he has an experimental setup that is very, very nice. He has here a microchannel with a colloidal particle of about 1.5 micrometer. And in this microchannel, he can generate a potential energy landscape, like a double well via light. And the particles only go along the channel, so in one dimension, and he can track them. So with this setup, we can generate potential energy landscapes, we can track the particle, and we can do a lot of measuring. And so I asked him if he can generate a double well and measure basically these probabilities with me. And here's a video. So this is not the channel we used, but this is the only video I got from him. So here you have a wavy channel, but the actual experiment was performed with a straight channel, but I don't have a video of that. Okay, so this is the potential energy he generated in the tube, in the channel. So here is the channel length, basically. This is the axis along the channel. And here's the energy that the colloidal particle in the channel feels. And what we considered is a similar thing as in the numerical example. We wanted a path that goes from this minimum to that minimum. So like this, in some reasonable time. For this particular example, we chose 120 seconds. And then we measured from the experimental data the probability for the colloidal particle to stay inside until the end, inside this tube. And from this probability, we could get the exit rate for this finite radius. And as you can see, so the green line is the experimental exit rate from this tube. And the black dashed line is the theory. And you see that our theory describes the experimentally observed probability to stay in the tube quite well. And we also compared the probability density inside the tube of those that have never left. And you can see it also agrees, I think, reasonably well between theory and what we experimentally observed. And the important thing is, for the experimental data here and here, there's no fitting, nothing. It's just like histogramming the data and looking how many particles leave. So there is no fitting, nothing. And still we can get like these results. So it's very primitive measurements, which is good, because the important thing here is now that we can finally verify these theoretical, mathematical results. So in the beginning, I told you that mathematicians look at this ratio of the tube probabilities, take the limit radius to 0, and define it as ratios of path probabilities. And they got a lot of results, and there are also different results actually. So different people on different approaches yielded different ratios of path probabilities. But because the probabilities of individual paths are 0, you could not distinguish between them, right? So the one guy calculates this ratio, the other guy calculates that ratio, and nobody can decide which one is the actual physical ratio, because you cannot measure it, because it's all probability 0 events. And with our approach, or with the tubes, we can now decide this, because what we think, or what we know, is that these tube probabilities are quantified by these exit rates that we can measure. And the idea is that you take the exit rate for two reference paths and radii at finite radius, then you can measure this without fitting any model, nothing. You just measure the data, and then you have measurements at several radii. You can extrapolate these measurements to 0, and then you can compare to these theoretical results. So this is kind of the idea. because we consider the finite radius, we have something we can measure, and this finite radius thing that we measured, we can then extrapolate to 0 without fitting a model or anything. And with this raw, more or less raw measurement, we can then look, does it agree with theoretical results on ratios of path probabilities? And so this is what we did. We considered, again, here's another picture of the channel that Yannis has. Here's again the free energy landscape. And what we did is we considered again the reference path. This is basically the same path as before, going from this minimum to that minimum. But now we took a faster one. It takes 20 seconds for this one. And we measured the exit rate difference for a path, for this path, and a path that stays here, a constant path. So we measured at radius 0.5 micrometer, 0.6 micrometer, 0.7 micrometer, 0.8 micrometer tube radii. We measured the exit rate for this and that path. We calculated the difference, and this is what the data gives us. And now at every time point, we extrapolate to radius 0. So here you have 4 points for 4 different radii. You can extrapolate to 0. Here you have 4 points for 4 different radii. You can extrapolate to 0 and so on. And you do this at every point in time here, and you get this point, this curve. So this is kind of the difference in exit rates measured experimentally at finite radius and extrapolated to 0. So we measured this at finite radius, then we extrapolated to 0, and we get this result. And we didn't fit a model for this. And now, according to the theory, this curve should agree with these ratios of path probabilities that people derived. So what we did is we took the potential energy that is fitted, we fitted a Langevin model from the data, and we evaluated these theoretical results on this fitted Langevin dynamics. And what we find is that one result for this ratio due to Onsager and Machlup agrees very well with the data. And there's also another theory where they say that this ratio is given by something different. And we also plot this here, and we see that one agrees very well with the data and the other one does not. So, I mean, just to reiterate, so this green line is for the first time, as far as we know, is a measured ratio of path probabilities for stochastic dynamics. And with this, we can basically address any question that anybody has ever had about path probabilities in stochastic dynamics. And the first question we addressed was, which of these theories actually describes path probabilities? And here is the answer. It's this theory by Onsager and Machlup, and the other one is, does not describe this system. And so this is kind of the story. This is, the idea is that with these finite radius tubes, we have a handle of approaching questions that have to do with individual trajectories, which we would not have otherwise, because individual trajectories have probability 0, and you need to have something that has probability not 0 to measure it, right? And so to summarize, so I told you a bit what soft matter is. It's mesoscopic systems where thermal energy is comparable to the typical energy scales in the system. And important model there is Langevin dynamics, which describes microscale systems coupled to an environment, like example water. And because no system in biology is isolated, you will always have some kind of Langevin applicability. And by considering ensembles of trajectories, by considering a tube full of trajectories, we can get non-zero probabilities, which can be used as a experimentally accessible vehicle to approach the question, to approach path probabilities. And we think that from a practical point of view, having these ensembles is also more natural than looking at individual trajectories, because there's always some threshold up to which you're interested in something. And with that, I want to thank the people that pay me and give me intellectual support, Mike Cates and Ronald Joy. And I thank you all for still having stuck around. And yeah.
Okay.
That's it.
Thank you, Julian. There is a question for you here. I'll take that before Sam takes his. And he says, how did you do the extrapolation to R equals 0?
Yes, okay. So, so basically I have these curves, and Oh, thanks for applauding. So basically, so if you measure this, then you have these time series, right? So at every, so you can, for example, interpolate, and they're on a discrete set lattice on time. So I mean, this looks continuous, but because it's experimental measurement, it's actually discrete time, right? So say at 10, we have now 4 data points. We have the exit rate for this radius, this radius, this radius, and this radius. So if you now took, for example, at one individual time, these data points and plotted them, so here you have radius now, here you have exit rate, you would get something like this. And then we fit a quadratic function through it, and then we extrapolate it to 0. So basically at every time we fit a quadratic polynomial or through the 4 data points, and we extrapolate it to 0. This is how we do it. Is this, does this make sense?
Tima, does that make sense? And Sally?
No. Of course, sorry. I mean, it's always a quadratic function, but of course, at every point we have different values for the exit rate. So it will be, so for every point here, we have a quadratic fit.
Okay, so does that answer the same? Yeah, the same quadratic for all points. Yeah, thanks. Okay, Savas, please, can you unmute and go on?
Hello, many thanks for this presentation. I really enjoyed it. And also you said you are being modest because you say it's a reasonably well comparison between experiment, but I think it's excellent based on the plots I've seen. Now, I'm very interested because apart from biological systems, I suppose ideas like that can also be applied in more macroscopic systems. I'm thinking of combustion engines, turbulence, this kind of stuff. I wonder, your system has this Langevin dynamics, which are already used actually in turbulent theories for a long time. I wonder if your system can be extended with having a mean flow in the background. So on top of, so imagining a particle that is being dispersed in a flow with a mean velocity, and then you let some random motion, Brownian, happening at the same time.
I mean, if you can use the normal Langevin equation and just have a different external force, then it's possible. I mean, you can add any deterministic force to the dynamics. Or is this what you had in mind, or?
Well, I wasn't thinking that as in terms of force, but I suppose, yeah, you can add it as an acceleration term you had in the first equation you showed. Oh.
Yeah, but in principle, I mean, the formalism is applicable whenever the Langevin equation is applicable. And yeah, so I think it would be possible, yes.
And also, is such a calculation for just one trajectory expensive?
What do you mean now? Which?
In the sense that if you imagine a pipe flow that is some millimeters in diameter, and I would like to see, I would like to occupy the full volume of this pipe flow and see what will happen in the individual trajectories in this pipe. Would that be expensive, considering that you're taking a radius of 1 micrometer in order of magnitude? If you want to simulate a millimeter, that means you need at least 1,000 trajectories. So I would like to have an estimate of how expensive it would be.
I mean, I can tell you that I'm not sure I understood the question correctly, but I mean, getting these experimental, I mean, for example, this one on the lower right corner, the green line, it takes some time. You have to really work with the data, and we had to come up with a protocol to extract this. So it's not something you just do a calculation and then a second later it's done. It took a long time to get this curve like that.
I'm actually referring to solving the equation.
Fokker-Planck. So I mean, you mean this one? So
for instance, yeah.
I mean, this is a single particle dynamics, right? So I'm just considering Langevin dynamics in one dimension for one particle, and yeah, so this takes a couple of minutes, I would say. It's okay for doing stuff like this, but if you wanted to do it on an industrial scale, like with a minimizer or whatever, you would probably have to think a bit more.
I see. Thank you.
Yes, this is what is all inertialess. Does this lead to a question? Or maybe I can comment. So Sam asked, did you say this was inertialess? So this is all overdamped Langevin dynamics. And actually we are working on underdamped Langevin equation. So when you have the mass as well, then what happens is when you have a very, very small tube radius, you will see qualitatively different behavior, right? Because if you have a finite mass system, then at very, very short times, you will always have ballistic motion because the inertia will always dominate. So we expect that if we have Langevin dynamics with mass, and we're actually doing the calculation, or one PhD student is doing the calculation, we expect that at small radius something different will happen, and that yeah, that there's something else at play. And of course, in the experiments, we don't see this because the smallest radius that we consider for measuring the exit rate is still so large that you don't see any inertial effects. So in a sense, this is now a bit, so in a sense, it's not the true probability, because the true probability would have to do with inertial effects as well. But then again, it's always the question, what is the probability and how do you quantify it, and what is measurable and what is reality, right? In the end, you need to look at the quarks of the stuff, yeah. So, but yeah, it's inertialess.
Okay. Do we have any more questions? Okay, in the absence of any, I must say to Dr. Julian that we're very, very impressed with your presentation. Like Sava said, you were being very modest. That was a very wonderful presentation. And thanks so much for taking out time to do this. Thanks for honoring us with your presence this evening. So on behalf of the MCR, we say a very big thank you.
Yeah, I thank you all for having me and for staying around, and yeah, and it was nice to hear you again, Savas. And I hope
Thank you.